Hi, I'm Paolo De Angelis and I'm a PhD student working on the small lab group. And with this video, I'm going to present my work on multi-scale modeling or lithium-ion batteries to study the aging phenomena. We are changing our development model, moving from fossil fuel to renewable energy. This opens many different challenges. One of these is to find a sustainable, safe, and reliable way to storage energy. The most promising technology nowadays is lithium-ion batteries. Usually they are made by an anode that is storing the lithium during the charging phase, an electrolyte composed by a lithium salt and organic solvent, a separator that avoids shortcut between the two electrodes, and a cathode usually made by a transition metal that accepts and releases lithium atoms in its crystal lattice. When we are charging a battery, the ions from the cathode diffuse into the electrolyte and percolate in the anode, vice versa when it's discharged. Unfortunately, some lithium react with the solvent during the charging phase, causing many side products, namely organic and organic salt, forming a passive layer on the anode surface called the SEI, solid electrolyte interface. This layer grows each cycle, causing the battery capacity fade that we experience with our electronic device. Since the higher activity of this layer is tough to study experimentally, and even modeling is not so easy because it requires the coupling of different scales, from quantum mechanics to manufacturing models. For this reason, the European Union financed the project Big Map, which brings together all the expertise required to model and study this phenomenon and boost the research and discovery of new batteries. And we are involved in it with the contribution of our bottom-up multi-scale model or SEI. As said before, the SEI results from the electrolyte dissociation, which requires the modeling of the electrons and therefore the use of quantum theory. Unfortunately, even using approximated solutions like density functional theory, the calculation is very time consuming, and in the best case, we can compute the reaction only for few molecules and for few picoseconds. To bypass these constraints, we decided to use reactive molecular dynamics, which has the advantage of solving the motion of atoms using the fast algorithm well known in classical molecular dynamics. But thanks to the reactive force field, which is designed and tuned to mimic the result observed in the FT simulation, the atoms can make and break bonds. Consequently, we can describe a bigger realistic system and observe the formation of molecules that are forming the SEI. Then, using in-house code that can reproduce the SEI, we build many systems with different layer thickness, and consequently, different battery degradation conditions. And from this model, we are computing the free energy escape and other microscopic quantities that are useful to other researchers. To conclude, on the hope that my model and research can be a starting point, all my simulations are wrapped in a Jupyter notebook, thanks to a library that I wrote in Python. In this way, all the effort that I put in my PhD will be helpful to other researchers that will push forward the human knowledge border.